Till now we have seen the procedure to write the output expression of a multiplexer. Now I will discuss about the exact opposite of that one. That means suppose I have some function, I want to implement that one by using a multiplexer. I have a function and I want to implement that one by using a multiplexer. Function implementation by using a multiplexer. Implementing a function using multiplexer, Mux. Suppose let us take a function like this. Let us take one function like this. This can be implemented with any type of mux, it doesn't matter. This can be implemented with 4 by 1, 8 by 1, 16 by 1, 2 by 1. Here I will tell you the procedure to implement this one by using multiplexers. Here the number of variables are 3, A, B, C. It contains 3 variables. So sigma of min terms, sorry, here m is missing. Small m means min terms. Here the number of variables are 3. The general procedure is like this. Suppose I am implementing a n variable function. N variable function. Whenever you go for 2 power n by 1 mux, n variable function, I want to design that one by using 2 power n by 1 mux, or 2 power n plus 1 by 1 by, sorry, 2 power n plus 1 by 1 mux, or 2 power n plus 2 by 1 mux, and so on. Whenever you want to use these type of multiplexers, there is no limit for it. Whenever a n variable function is implemented by using this one or this one or this one, just that mux is enough. No extra gates are needed. Just that mux is enough. So only one mux is enough. Just that mux is enough. No extra gates, nothing. That's about implementation by using these type of multiplexers. Suppose if you want to implement with 2 power n minus 1 by 1 mux, 2 power n minus 2 by 1 mux, and so on. In this case, for some functions, extra gates are needed. For some functions, extra gates are needed. Don't think that every time extra gates are needed whenever we use this type of multiplexer. That depends on the function. For some functions just that mux is enough. For some functions they may require some other gates. That depends on the function. That's why for some functions, I am not saying every function require extra gates. For some functions it may require extra gates. Just I will explain this concept through this example, then you can understand what I am trying to tell. Suppose here n equal to 3. Then 2 power n by 1 mux means 2 power 3 by 1 mux. That means 8 by 1 mux. 2 power n plus 1 means 2 power 4 into 1. That means 16 by 1 mux, and so on. Now, if you implement a 3 variable function by using 8 by 1, 16 by 1, and the next size 32 by 1, and so on, only that mux is enough. No extra gates are required. That mux is enough. Now, if we use 2 power n minus 1 means like this, a 4 by 1 mux or a 2 by 1 mux and so on. I am implementing a 3 variable function using 4 by 1 or 2 by 1. Then for some functions it may require extra gates. Now I will implement this one by using different approaches. Suppose let us take a 2 power n by 1 mux. I want to implement this one by using 2 power n by 1 mux. Here n is 3, that's why 2 power 3 by 1 mux. That means 8 by 1 mux. 3 variable function by using 8 by 1 mux. 8 by 1 means 8 inputs will be there. 3 selection terminals. So here the meaning of this one is sigma of minterms 0, 1, 4, 7. That means it is sum of minterm 0, minterm 1, minterm 4, minterm 7. This function is sum of these 4 minterms. And some time back we have seen the mux output expression. Always mux output is like this. Minterm 0 into input 0, minterm 1 into input 1, minterm 2 into input 2, minterm 3 into input 3, like this. Minterm 4 into input 4. Always multiply minterm and input and add those products. If it is 8 by 1 mux, this is the exact expression. If you observe carefully, this is the expression I want. So here I need M0. That means here M0 should be present. That means whenever I0 is 1, 1 into M0, M0. That means when I0 is 1, then it will be M0 into 1, so M0 will come. I need M1, so give 1 to I1 terminals, so M1 into 1. Then observe carefully, I don't want M2, so I don't want it, so give 0, so 0 into M2 will be 0, so here apply 0, so M2 into 0 plus, I don't want M3, so M3 also should be 0 plus, I need a M4, so apply 1, so M4 into 1. I don't want M5, so M5 into 0. I don't want M6, M6 into 0. I need M7, so M7 into 1. So that means like this you have to give the input. So after multiplication, it will be like this. That's what I need. So that's the implementation procedure. Instead of thinking in a lengthy manner like this, one simple procedure is always the input variables must be given to selection, and at these positions, that is at position 0, 1, 4, 7, at position 0, 1, 4, 7, apply 1. This is 0 position, 1 position, 4 position and 7 position. Apply 1 and remaining values will be 0. That's all. Remaining values will be 0. That's a simple procedure. At these positions, apply 1, remaining will be 0. Connect these variables to the selection. That's all. That's about designing by using 2 power n by 1 mux. Now we will design this one by using 2 power n plus 1 by 1 mux. Now I am designing this one by using 2 power n plus 1 by 1 mux. Here in this case n equal to 3 variables are there. So 2 power n plus 1 means 2 power 4 by 1 mux. So take a 16 by 1 mux. 2 power 4 means 16 by 1 mux. So 16 inputs will be there, 4 selection variables, and the implementation procedure is maintain S3 will at 0, connect ABC here. S2, S1, S0 must be ABC, and S3 is always 0, and at these positions apply 1, that is at positions 0, 1, 4, 7, apply 1, remaining will be 0. Actually just write up to this point, no need to write zeros at all here, because anyway they will not come. The reason is, if you observe carefully, S3 is maintained permanently to 0. S3 is permanently connected to 0. So that means always the different combinations we can apply is like this. Only these combinations are applied to this mux. That is 0 to 7 are applied to this mux. Remaining combinations are never applied. So that's why don't bother about 8 to 15 input terminals. Whether you give 0 or 1 here, it doesn't matter actually. It doesn't matter. Just think up to this point, up to 7. Whether you give 0 or 1 here, it doesn't matter, because those combinations never applied here, never come here. That's the reason. So like this we can design by using 16 by 1 mux. Just use only first 8 terminals, that's enough. Think like a 3 by 1 mux. Think like a 8 by 1 mux. Only use first 8 terminals. Here maintain S3 at 0, here ABC. That's all. Suppose even if you go for 32 by 1 mux, 32 by 1 mux means here 5 selection terminals will be there. 5 selection terminals. And S2, S1, S0 will be ABC, and maintain this at 0. That is S3, S4 will be 0. And here 32 inputs are there. Only use the first 8 inputs. Don't bother about the remaining input terminals. Just think about only first 8. The first 8 connections must be like this. Don't bother about the remaining, and the selection must be like this. That's the procedure if you go for 32 by 1 mux. So like this you can design this function with 2 power n by 1, 2 power n plus 1 by 1, 2 power n plus 2 by 1, and so on. No extra gates are needed. The reason is here just ABC are needed, either 0, 1 are needed in the input side. So there is no A bar, there is no B bar, there is no C bar, just ABC. So that's why no extra gates, just that mux is enough. No need of any extra gates whenever you go for this type of mux. Next I will design this one by using 2 power n by 1 mux. Here n equal to 3 variables are there. 2 power n minus 1 means 4 by 1 mux. 4 by 1 mux. So take a 4x1 mux. Sorry, only two selection inputs will be there. So here 3 variables are there in the function, but here only 2 selection. So only use 2 out of these 3 here. Just use 2 here. The third variable will be used here now. 2 variables here, 1 variable here. 1 variable as input, 2 variables as selection. You can use any 2 here, it doesn't matter. Suppose if you apply BC here, A will be connected here. Now I will verify whether it is A or A bar should be given here. To identify the input, one approach is that we have to form one table here. Here I want to identify I0 to I3. So in this side write inputs. These are the values I want to find. Already I connected BC here and remaining variable is A. Write different combinations of A. Here write different combinations of A. The different combinations are either A bar, A. So A bar, A. Actually this mux is controlled by BC. That means when BC is 0, 0, I0 will be selected. BC is 0, 1, I1 will be selected. BC is 1, 0, I2 will be selected like this. So actually this side is BC. So when BC is 0, 0, I0 is selected. BC is 0, 1, I1 is selected. BC is 1, 0, I2 is selected. BC is 1, 1, I3 is selected. Similarly, here write the zeros and ones here, bit values. So A bar means 0, bar means 0, always variable means 1, bar means 0. So A bar means 0, A means 1. Write the values. First write like this. After that, at each position, write the ABC value. ABC value in decimal format. ABC value in decimal. ABC, the reason for ABC order is, here he said that A is MSB terminal. He said that A is given as first terminal means this is MSB. So follow the same order, ABC. That's why ABC, that's the reason. He said that A is the first variable, that is MSB terminal, most significant bit. That's why follow the same order. So here this side is A, this side is BC. So at this position, A value is 0 and BC are 0, 0. So ABC is 0, 0, 0. A is 0, BC is 0, 0. So 3 zeros. So 3 zeros means decimal equivalent is 0. Here ABC is 0, 0, 1. A is 0, BC are 0, 1. 0, 0, 1. So 1. And here ABC is 0, 1, 0. 0, 1, 0. So 2. Then here the value is 0, 1, 1. So 3. 0, 1, 1 is 3. Here ABC is 1, 0, 0. 4. 1, 0, 1. 5. 1, 1, 0. 6. 1, 1, 1. So 7. 3 ones means 7. Then write the values like this, ABC values at each position. And here actually this is the function I want to implement. Sum of minterms 0, 1, 4, 7. So circle those numbers here. 0, 1, 4, 7 should be circled. That's the next step. Circle 0, 1, 4, 7 in this table. 0, 1, 4, 7. Circle those numbers. The next step is circle these numbers in the table. Now I0 is obtained from 0 and 4. I1 is obtained from 1 and 5. I2 is obtained from 2 and 6. I3 is obtained from 3, 7. Just observe these two numbers. I0 is obtained from 0 and 4. Whenever both are circled, the input will be 1. Whenever both are circled, the input will be 1. So, since 0 and 4 are circled, input is 1. And if you observe the next values 1, 5, only one number is circled. When both are circled, we have to write 1. When only one number is circled, write the row variable. For this row, variable is a bar. Because the circle number is here, the corresponding row variable is a bar. So a bar. If only one circle is there, write the row variable of that circled number. So here 1 is circled, the corresponding row variable is a bar. When both are not circled, 0. If you observe, I2 is obtained from these two numbers. These two are not circled, so 0. When both are circled, 1. Both are not circled, 0. And here, only one circle is there. Write the row variable. The corresponding row variable is A. So 7 is circled. That's why row variable is A. So like this, we have to identify the input expressions. So the connections are like this: 1 A bar, 0 A. So I0 is 1, I1 is A bar, I2 is 0, I3 is A. That's a implementation of this function using 4-band mux. If you observe carefully, here A bar is there. So we require one NOT gate. That means in addition to this mux, one NOT gate is also needed. That's what extra gates. So whenever you go for 2 power n plus 1, 2 power n by 1, 2 power n plus 1 by 1 and so on, that mux is enough. Whenever you go for 2 power n minus 1 by 1 mux, 2 power n minus 2 by 1 mux and so on, you require extra gates. Don't think that every time extra gates are needed. For some functions, they are needed. So here one NOT gate is needed in addition to mux. So here I have selected BC for selection. No need to take BC, you can take AC or AB, it doesn't matter. Now I will explain that point also. Suppose I selected, I am applying AC for selection. Suppose I am applying AC for selection. Now see what happens. So here the remaining variable is B. So this side is the remaining variable combination. So B bar B. B bar means 0, B means 1. That's a value, binary value. Now this mux is controlled by AC. So this side is AC. When AC is 0, 0, I0 is selected. AC is 0, 1, I1 is selected. AC is 1, 0, I2 is selected. AC is 1, 1, I3 is selected. Now write the ABC value. Always follow this order: ABC, MSB to LSB, most significant to least significant. Always write the ABC value. So if you observe carefully, this is A value. This is because it is, this side is AC. This is A value, this is B value, this is C value. So ABC will be 0, 0, 0. So 0, 3 zeros, 0. At this position ABC value is 0. At this position ABC value is 0, 0, 1, 0, 0, 1. So 1. This is A, this is B, this is C. So 0, 0, 1. So 1. At this position ABC is 1, 0, 0. See, A is 1, B is 0, C is 0, 1, 0, 0. 1, 0, 0 means 4. 1, 0, 0 means 4. Here ABC value is 1, 0, 1. 1, 0, 1. So 1, 0, 1 means 5. Like this, we can write the numbers. The order will change. In the previous case, the order is different. In the previous case, it came like this. Whenever A is used for mux input, this is the order we got. Here 0, 1, 2, 3, 4, 5, 6, 7, but this order is different. 0, 1, 4, 5 is the first row. 2, 3, 6, 7 is the second row. So that's why whenever this selection is changed, automatically the order will change. Be careful. Don't think that always this is the order we have to write. That depends on the selection. So after forming this table, then circle these numbers. Circle 0, 1, 4, 7. So 0, 1, 4, 7. So here only one circle is there, that's why B bar. Here also only one circle is there, so B bar. Here also one circle is there, B bar. Here one circle is there, so B. So like this. Finally, this is the mux input when ACR selection. Similarly, we can connect AB here, and C will be here. AB here and C will be here. Just follow the same procedure. Now write C here, C bar C. This side is AB. Once again, you will get a different order. So I will write that order also. You can verify on your own. When A is used, this is the order. When A is used as input, this is the order. When B is used as input, the order is like this. If C is used as input, the order will be in this manner. 0, 1, 2, 3, 4, 5, 6, 7 like this. Just follow these tables. If you remember, it's better. Okay. Whenever A is used, it should be like this. B is used like this. C is used, it should be like this. Remember these tables. That's about implementing by using 4x1 mux. Now I am still reducing the size of the mux. Now I implemented by using this one. Now I implement by using this one. 2 power n minus 2. Here n is 3. So 2 power n minus 2 by 1 means, in this case, a 2 by 1 mux. In this case, a 2 by 1 mux. So here the procedure is similar to the previous procedure. Take a 2 by 1 mux. Only one selection will be there. Only two inputs. The procedure we followed for 4 by 1 is we formed one table and we circled. Yes, follow the same procedure. We form one table. Here only two inputs I want to find, I0, I1. Always this side is the inputs I want to find. So here 3 variables are there, but only one selection. So out of these 3, one will be connected here. It doesn't matter, we can choose A, B, C, doesn't matter. Here I am choosing A. So remaining variables are BC. So they are connected here. They are connected to I0 and I1. So remaining variables are BC. So write the remaining variable combinations. So here remaining variables are BC. The different combinations are B bar, C bar, B bar, C, BC bar and BC. They are the remaining combinations. This side is A. When A is 0, I0 is selected. A is 1, I1 is selected. And B bar, C bar means 0, 0. B bar, C means 0, 1, 1, 0, 1. They are the corresponding binary numbers. Now the next step is always write the ABC value at each position. Here ABC value is 0 because A is 0, BC is 0, 0, 0. Here ABC value is 0, 0, 1, so 1. Here ABC value is 0, 1, 0, 2. Here ABC value is 0, 1, 1, 3. Here ABC value is 1, 0, 0, 4, like this. Now circle these numbers in the table 0, 1, 4, 7. Now I0 is identified from this column, I1 is identified from this column. So here I0 is equal to, just observe this column, 2 circles are there. Whenever one circle is there, take that term. If one more circle is there, take the term also. Just add all those terms. So here this term is circled. That's why B bar, C bar, take this term. Take the corresponding row. And this is also circled. So write that one also. B bar C. We can simplify these two terms. B bar is common. So C plus C bar is 1. So after simplification, it will be B bar. That's about I0. I1 is, here 4 is circled. That's why you have to write this term. And 7 is also circled. So you have to write this term. BC plus B bar C bar means it's XNOR. So B XNOR C. B XNOR C. So that's about I0 and I1. Connect accordingly. So here B bar should be applied. Here XNOR of BC should be applied. B XNOR, sorry, XNOR. This is the symbol for XNOR. Like this we can design by using 2 by 1 multiplexer.